Alright students, so here we are. This is the review for the second Algebra 2 test, which at this point is coming up really quick. Today's Tuesday. This is the hurricane day, hurricane holiday. So let's get through this. Number one, g of x equals negative 1/4 x plus 7/4. Find the inverse of the function. So I can't fit the work here, and I'm not gonna turn this into a Morelli 10-hour video. We're just gonna solve the questions. Okay, I hear the round of applause in the background. But I gotta paste it over here because even writing small, it's oh, that can't be the whole review. Where's the second page? I'll find the second page in a minute. Okay, number one. So how do we find the inverse of this function? Well, let's do it. We're going to cross this out and replace it with a y. So now y equals negative 1/4 x plus 7/4. And now what we're going to do is swap the x and the y. So x equals negative 1/4 y plus 7/4. And now the big thing is just solve for y. Okay? So, step one, what would be, well, I'll just give you a second. What would you do for step one? Because most kids would say add 7/4 or subtract 7/4 from both sides. And that is perfectly valid. However, there's a trick here. Notice that the denominators are both 4. Okay, so here's, if we do this, if I was to write this instead as negative 1y plus 7 over 4, maybe you'd see the trick, because that's an equivalent expression, an equivalent equation to what's written above. Well, now all I've got to do is get rid of this 4 by multiplying both sides by 4 over 1. Okay, which on the left side would just be 4. So look what happens. Cancel, cancel. Yeah. Now I got rid of all the fractions. That's what it saves us a step. Makes it a lot easier. Now I've got negative 1y plus 7. 4x equals negative 1y plus 7. And we subtract 7 from both sides, which gives me 4x minus 7 equals negative 1y. Okay, now the quick and dirty method here is to just change all the signs. Plus, plus, minus. Okay, but if you find that confusing, then the mathematical thing to do is to divide everything by negative 1. Okay, so we divide here, here, and here by negative 1. And you end up with exactly what the quick and dirty method was, which is just negative 4x plus 7 equals y. Reflectivity property says that that's equal to negative 4x plus 7, putting y on the left side. Therefore, remember this is the therefore symbol. Therefore, g inverse x, remember that's how we write g inverse x equals negative 4x plus 7. Okay, so g inverse x equals negative 4x plus 7, that's number one. G inverse x equals negative 4x plus 7. Okay, if that's all you write, there's no credit given. Or yeah, that's the rule in pre-AP, no credit given at all. So we need scratch paper showing the work. Number two, moving on to number 2, ladies and gentlemen. F of x equals x over 4 minus 3. Okay, I think I can just remember that. F of x equals x over 4 minus 3. So instead of copying, let me just create here a line. F of x equals x over 4 minus 3. So this is number 2. F of x, I already forgot. X over 4 minus 3. Okay. X over 4 minus 3. Okay, what do we do? Find the inverse. Okay. Cross this out, write y equals x over 4 minus 3. So what's next? Swap the y and the x. So now x equals y over 4 minus 3. And we just solve for y. Okay, so what would you do? Add 3 to both sides. Yep. And then multiply everything by 4. Simple. So let's do that. We'll add 3 to both sides. X plus 3 equals y over 4. And now what we'll do is multiply both sides by 4 over 1, which on the left would just be 4. Okay? And the benefit there is we cancel the y's, the 4's, and now we have y alone equals, and now what we need to do is the distributive property. Okay, distribute that 4, and so you get 4x plus 3 equals y. The reflectivity property of equality says I can rewrite that as y equals 4x plus 3. Right, just to get the y on the left, and then this was a function of x, so therefore get into the habit of using this symbol and it'll make you feel smarter. F inverse x equals 4x plus 3. So F inverse x equals 4x plus 3. F inverse x equals 4x plus 3. F inverse x equals, I already forgot, 4x plus 3. Okay. We're flying through this. That was easy. Find the inverse of each function. Graph the original function as its inverse. State the point of intersection. This would be the solution of the system. Okay. So do the same thing we just did, only graph it on this ridiculous graph. It's hard to read. And then state the point of intersection, which would be the solution of the system. And I guess the reason we're doing this is because we're leading into solving systems of equations, which is just where the two lines intersect. Okay, so number three. Let me spin this sucker around. Oh, come on. All right. And g of x equals 2x plus 4. Moving in. Number 3, g of x equals 2x plus 4. So first they want us to find the inverse. Then they want us to graph the original function and its inverse, and then identify the point of intersection, which would be the solution to the system of equations formed by the function and its inverse. Okay? Let's do it. So this becomes y equals 2x plus 4. Now we swap the x's and the y's, so x equals 2y plus 4. And we solve for y. Minus 4, minus 4. X minus 4 equals 2y. And what we'll do is divide everything by 2. I'm writing a little sloppy for my taste. Let's get let's get a little bit, let's tighten it up, Morelli. Now it's very useful here to put a 1 next to the x, so you know that that leading slope is 1/2. Right. So let's see what we got. Pardon me. We have, and let's try to write this in slope-intercept form. We have 1 over 2x minus, and then 4 divided by 2 is 2, minus 2 equals y. Reflectivity property of equality states that y equals the same thing, so y equals 1/2 x minus 2, and we assigned g of x to y, so the inverse function would be g inverse x. So we can say, therefore, function g inverse x equals 1/2 x minus 2. Okay? So now they want us to graph both functions. So first, let's write that down. G inverse x equals 1/2 x minus 2. So first, let's write like the first thing they want, which is G inverse x equals 1/2 x minus 2. Okay, and now they want us to graph both functions. Okay, so let's do that. Let me make let's pick some colors here. So I'm going to graph the original function in green, and we might as well use red for the inverse function. So in green, let me make it tiny. The y-intercept here is at 4, and the slope is 2 over 1. So from here, I go up 2 over 1, up 2 over 1, up 2 over 1. I can even go down 2 to the left 1, 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 down 2 to the left 1. Okay? In other words, I'm forming a line. I should be able to put a ruler on that and have those points all line up. If they don't, we got a problem, and they do line up. Come on here. Okay, so let's draw that in. There's the original function. Make sure you put these arrowheads, otherwise you're indicating that it's not an infinite domain and range. Okay, so that is, and we always label, this is g of x equals 2x plus 4. All right, and so now we're going to plot the inverse function, 1/2 x minus 2. So the negative 2 there is the y-intercept, and I go up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. Could even go down 1 over 2 to the left, down 1 over 2 to the left. Bingo, there's the intersection point, down 1 over 2 to the left, down 1 over 2 to the left, down 1 over 2 to the left. Okay? So let's plot that in. I need to order all of your rulers, protractors, clear, something clear that you can see through. That's the best kind, those clear protractors. Let's see. All right. Draw this in. Perfect. So let's put the arrowheads on the end, label it G inverse x equals 1/2 x minus 2. And now let's get back to our, so we're going to identify this point. This is the solution to the system of linear equations, which is -4 comma -4. So let's identify that point. Let's use another color. How about orange? So let's make sure that that's pointed out as -4, comma, -4. All right, so here's what we're going to write. We're going to write the solution to the system of g of x and g inverse x is 4, comma, -4, comma, -4. There it is. So that's part 2, all right? Well, actually, I guess graphing it was part 2, and then this is part 3. So they want you to do 3 things. Find the inverse, graph both functions, identify the intersection point, and then, you know, kind of like state it. That's the solution to the system of g of x and g inverse x. Great stuff. Okay, well that was easy. Moving on to number 4. Man, if the test is this easy, everybody's going to make 100. So number 4, ladies and gentlemen. Number 4, f of x equals 1 plus 1/2 x. Aha! You know, right away, before we do anything, I would just rewrite this because they're messing with you. F of x equals 1/2 x plus 1. See, 1 plus 1/2 x isn't in a graphable form, right? You can't graph that. So anyway, let's take that and go find its inverse, and then we'll graph the 2 functions and we'll find the intersection point, blah, blah, blah. Okay, so, okay, just section off some space here. Nope. All right, so number 4 gives us f of x equals 1/2 x plus 1, which is the same as 1 plus 1/2 x. Okay, I'm writing it this way because this is slope-intercept form. So now I'm going to cross that out and write y. Remember, we're finding the inverse. Y equals 1/2 x plus 1. Now I'm going to swap the x and the y, so x equals 1/2 y plus 1. Subtract 1 from both sides and multiply everything by 2. So x minus 1 equals 1/2 y. Now we're going to multiply both sides by 2 over 1. So times 2 times 2. On the right, that cancels out, leaving y by itself. Y equals 2 open parentheses x minus 1. And what we're going to do is distribute the 2, leaving 2x minus 2 equals y. Reflectivity property of equality, y equals 2x minus 2. And since this function was originally f of x, and we assigned f of x to y, therefore, f inverse x, okay, the inverse function of x, is 2x minus 2. Okay? So now we've got the inverse function, so let's go write that. 2x minus 2. So first things first, we've got the inverse function. F inverse x equals 2x minus 2. And I guess I'll stick with my labeling scheme. So I'll label the original function, which I'll use this one. This will be green. And then I'll do this one in red, just so we know. So first the green. Let's graph this. So I've got a y-intercept at 1. Okay, so that's 2, 4, 6. So this is 1. And then my slope is 1/2, so up 1 over 2. Up 1 over 2. Wait, hold on, I just did that wrong. Up up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. Okay, down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. Okay, you don't have to plot all those points, but it helps. Okay, so they should all line up. Perfect, 27 degrees. If we were to go into depth on the stuff I was teaching you or talking to you about imaginary numbers, I could show you how to figure out what degree that would be. At 27 degrees has a name, but we'll talk about it later. Okay, so this is f of x equals 1/2 x plus 1. So now let's graph f inverse x. So that's 2x minus 2. So this one's going to start at -2, and it's going to go up 2 over 1. Up 2 over 1. There's the intersection point. Up 2 over 1. Up 2 over 1. Up 2 over 1. Let's go back here and then go down 2 over 1. Down 2 over 1. Down 2 over 1. Down 2 over 1. Okay? Bring in our ruler. (63 degrees). So originally, remember that it's 27 degrees, the green line, and this one's 63 degrees. That's interesting. Is there any way you could have predicted that using some cool mathematics that we could learn? Yep. Okay, so now we stated the inverse, we graphed the functions, and now what we're going to do is identify the point of intersection. I think we were using orange for that. So here's that point. What is that point? 2, 2? Okay. Just going to this is 2, 2. And what we write is the solution. You have to write this out. To the system of f of x and its inverse and f inverse x is 2, 2. Bingo. Done. All right. Okay, and number 5, we're asked to prove if the given functions are inverses. Now, you guys know what that means. That means that 44-minute video that you watched, if you didn't watch it, you should have watched it. If you didn't watch it, you don't know what we're about to do. What we have to prove, this is the question. What do you do to prove? How do you prove? Here's all you have to do. You have to prove. I'll write it up here. Here's a little rule. This is called the validation rule. You need to write this down. Okay, commit it to memory. Validation. Okay. If H, I'm using these two, it's H of f of x equals f of h of x equals x, then h of x and f of x are inverses. Okay, so this is called, these two things here. This is called composition of functions. And what you're looking for is you want both of them to equal x. So you want h of f of x to equal x, and then you also want f of h of x to equal x. They both have to equal x, and that means they're both equal to each other, therefore they're both inverse. That's inverses of one another, okay? So that's the proof. So we're going to run through 5 and 6, and then We're going to use that validation rule, okay? Okay, so this is a quick section here where I'm going to reiterate the proof. How do you prove two functions are inverses? Okay, so I wrote this all out. I would write this down if I were you. I'll read it to you so you know what it says. The validation rule. If the composition of function A and B, in other words, A of B, equals the composition of function B and A, in other words, B of A, and both of those equal X, then A and B are inverses. In other words, if A of B equals X and B of A equals X, then A and B are inverses. Okay? I've sectioned this off as its own section in the video because if this isn't in your brain, you can't do those two problems. End of story. Okay, students, so here we are with number 5. And remember, we're trying to prove whether these two functions are in fact inverses of each other. We have h of x equals negative 2x minus 1 and f of x equals negative 1/2 x minus 1/2. We must use this validation rule. So what we're going to do is a two-step process. And here's step 1. I'd really like you to write it out just like this. Step 1, show that h of f of x equals x. So let's do that. We'll write h of f of x equals. Okay, now please write this out just like I write it. So I'm going to use the framework for function h, but stick in f of x for x. Okay, but do it just like I do it. Okay, please take this time to do this step. So negative 2, open parentheses, and then we're going to write in here f of x. Okay, we're going to take this extra step here just to write this out so you understand what you're doing. And what I'm about to do now is I'm going to take and substitute this for what's inside the parentheses, okay? And that's why I just want to show that step so you can show me and anyone else what you're doing. Now let's write out h of f of x equals negative 2. Big open parentheses because we got to put this fraction in. Negative 1 over 2x minus 1 over 2. Close parentheses, minus 1. Now here's something super cool, okay? We can make our lives so much easier right now. Oh boy, oh boy, oh boy. So notice something. I've got a negative 2 right here. And then I've got a negative fraction. I can cancel this whole negative 2, and I can cancel that negative and the 2, and that negative and the 2. I can cancel it all out, get rid of all of it, leaving behind x plus 1, okay? So that's a huge trick right there. So now I have h of f of x. Do you see you didn't have to distribute the negative 2 is the big deal there. Equals, and now I've canceled out the negatives and the 2's, just leaving x. And then remember, when you cancel out the negative inside, that makes this positive, okay? So it's going to be x plus 1. Now we don't need the parentheses, minus 1. 1 minus 1 is 0. Therefore, I love writing this symbol. H of f of x equals x. Big deal. Yay. Okay, so we confirmed part 1 of our validation rule. All right? Now we got to do step 2. Okay? Step 2. Show kind of the converse, right? Show that f of h of x also equals x. Okay, so I'm going to write f of h of x equals, and now I'm going to begin with the framework of f of x. So I'm going to write -1/2, open parentheses, and then stick in h of x, close parentheses, minus 1/2. So -1/2, so -1/2, open parentheses, and then I'm just going to write h of x, just so I show what I'm doing. And then I stick in a minus 1/2 at the end. Okay, and now I'm going to perform the substitution, right? So I'm going to substitute what h of x there, I'm going to substitute in what h of x equals, namely -2x minus 1. Okay, so I'm going to stick that inside the parentheses now. -2x minus 1, remember that. So f of h of x equals -1/2, open parentheses, and then it's -2x minus 1, close parentheses, minus 1/2. Let's just double check that that's correct. Yup. Okay. Now, is there anything we can do to avoid having to distribute the negative? This guy right here, is there anything we can do? Is there any trick we can exploit? No. Okay? Sometimes this is the answer is no. So we're going to just say f of h of x equals, and now we'll just distribute, -1/2 times -2x is going to equal +2/2x, right? And then I'm going to have a -1/2 times a -1, which is going to give me +1/2. And then I'm going to stick on the -1/2, which is from right here. Okay, so look here. 1/2 minus 1/2 is 0. Cancel, cancel. All that's left is x. Therefore, yay, f of h of x equals x. So now we prove the second part. So we proved both parts. So here's what we can write. Here's a conclusion, right? So this is the conclusion, the proof. This is the proof statement. Okay, here it is. Ready? I'm going to put it in orange. Since. Now there's a symbol for since. Did you know that? The symbol for since is the upside down version of therefore. So since. Okay, if you want to write it like that. Since h of f of x equals x, and f of h of x equals x, then h of f of x equals f of h of x equals x, therefore h of x and f of x are inverses. Now, when you finalize a proof, you put this symbol in here. It's a little black square. Okay? And what this little black square means is end of proof. Okay? So if you want to be really mathematically cool, put that little black square at the end, because that means your proof is done. And we're done with this problem. So let's go back to our actual paper. And I guess we just have to say like see attached work. You know, however, h of x and f of x are inverses. Okay, and that's the end of number 5. All right, students, here we are looking at number 6. Now, this is coming directly from the paper. I just rewrote it. So here's what it looks like for you. And I just rewrote it, okay? So given f of x equals negative x over 2 and g of x equals negative x plus 1 over 3, prove that f and g are inverses. And what we're going to be referring to here again is this validation rule, okay? The rule is if the first of the second equals the second of the first equals x, then both the first and the second functions are inverses. So we have a two-step process, ladies and gentlemen, and we will begin with step number 1. Step 1. Okay? It's very important to write this out. Step 1. What are you doing in step 1? Show that f of g of x equals x. Okay? That's what we're trying to do. So let's do it. Let's write f of g of x equals, and now use the frame of f of x. So what are we going to do? We're going to put a negative sign, and then we're going to put a big open parentheses in the numerator section. And then inside that parentheses, we're going to write g of x. And then we're going to close that parentheses. And then we're going to put a fraction bar. And then beneath that fraction bar, we're going to put a 2. Okay? Now in step, pardon me, in step 2, we're actually going to substitute this in here. Okay? So we're going to have to put a big fraction bar, because we're going to have to fit that whole fraction in the numerator. Okay, so now moving on. Let me get rid of those highlights. Moving on, f of g of x equals negative. Okay, now what my recommendation is, just put a huge open parentheses like this. And now what you're going to write in is negative x plus 1 you need a ruler for this, or a straight edge, over 2, or sorry, over 3. That was g of x. Okay, close the parentheses. And then don't forget the plus 1. Okay, wait, never mind. That's this. Okay, good. Now all of that goes over 2. See, it gets confusing. Okay, that's why it's important to write out every step. Okay, good. We're good to go. Now, a point of possible confusion, ladies and gentlemen. This is a negative 1, okay? And it is a numerator, okay? It's negative 1 over 1. And that's like everything your math teacher never told you, right? What do you do with the negative symbol? Well, you're going to multiply that to the numerator portion of this fraction, which itself is in the numerator of an even bigger fraction. Okay, so now we're going to distribute the negative 1 here and here. And we know that just means change the signs. Okay, so now we're going to write f of g of x equals. Now negative 1 times negative 1x, negative 1 times negative 1 is positive 1, so I just get x. Negative 1 times positive 1 is negative 1, so x minus 1. Ruler time, over 3. But wait, this is where it gets super confusing. Ruler time, all of that over 2. Okay, this notation is very confusing. So let's rewrite this using something we understand much better. Let's just write x minus 1 over 3. Let's say what we're doing, okay? What does the fraction bar do? It means division, right? So write divided by 2, right? So divided by 2 over 1. Well, what does that equal? We don't divide. We multiply by the reciprocal. So this is x minus 1 over 3. I didn't use my ruler. Okay, sorry. X minus 1 over 3 times 1 over 2. Okay, so what does that equal? Well, I guess we're distributing the 1, so that's just x minus 1 over 6. Okay, so what I have so far is I have f of g of x equals x minus 1 over 6. You know, another way you could write this is 1 over 6x minus 1/6. But notice what that doesn't equal. This does not equal x. So we could have made a mistake, but it also could be the case that they're not inverses. All right, so we did not show, we failed to show that in step 1, f of g of x equals x. Let's try it the other way around. Okay, so now let's try step 2. That's going to be g of f of x. Like, if we find out that this equals x, then we might want to go back and check our work. Okay, so part 2, what did I write? Am I doing parts or steps? I'm doing steps. So step 2, show the converse. Show that g of f of x equals x. Okay, so we're going to use g of f of x equals. Now we're going to use the framework of g of x. Now g of x was negative x plus 1 over 3. Negative x plus 1 over 3. Okay. And what I want to do, what I want to do is, I just want to delete the x. Come on. I want it to be like this. Negative open parentheses, close parentheses, plus 1 over 3. And inside, I want to write f of x. Okay? Now, inside that parentheses, I'm going to put what f of x is. So I'm going to replace that f of x with negative x over 2. Okay, in the next step. So g of f of x equals, and here I recommend writing out negative 1. See, instead of that minus sign, I would write out open parentheses negative 1, just so you know what you're doing. And then you're going to do a huge parentheses, and you're going to write down what f of x is, which is negative x over 2. Negative x over 2. Okay. Now close that parentheses off. Don't forget about this plus 1. And put the whole thing over 3. Okay. Now what are we going to do next? We are going to recognize that this is negative 1 over 1 times negative x over 2. So I'm going to distribute multiply the negative 1 to the negative x. That's a negative 1x. So that's going to turn that into a positive x over 2 plus 1 on the top. Anyway, we'll get there. So here comes g of f of x equals. Okay. And I'll even make this simpler. So we're going to have positive 1 up there, right? So this is going to be 1 over 2x plus, and here I'm going to take 1 and I'm going to say, well, that's 2 over 2, right? And then I'll let me combine these together and see if that does anything. I don't see this going the right way. This isn't looking good, folks. Over 3. Like, I don't see this resolving down to x, but I'll just check it anyway. So now that I've done this common denominator thing up here, I can rewrite the top as x plus 2 over 2 okay, and then I'm dividing by 3, right? So dividing by 3 over 1, which is just another way of saying x plus 2 over 2 times 1/3, because we multiply by the reciprocal. Okay, so that gives me x plus 2 over 6. So what I have g of f of x equals x plus 2 over 6. Which is also the same thing as saying 1/6 x plus 1/3, because 2/6 reduces to 1/3. But either way you write it, what does it not equal? It does not equal x. So don't listen. The temptation here is to say, wow, we wasted a lot of time. No, you didn't. You're simply asked to prove something, right? So finding that the proof is false is just as interesting and valuable as finding that it's true. So we're still going to write a conclusion. So here's our conclusion. Okay. I mean, we still proved something. Okay, so here's our conclusion. This is the proof statement. I know it's more exciting to prove that it is true or that they are inverses. So here's our conclusion. We're going to use some cool language, some cool symbols here. Since, okay, since, I want y'all to get into the habit of using these symbols. Since f of g of x does not equal x, and since g of f of x does not equal x, we can even say further, and since f of g of x did not even equal g of f of x. You know, those were different, if you remember. Like, this one had 1/6x plus 1/3, and this one was 1/6x minus 1/6. So they don't even equal each other, right? So none of these can get conditions. So this does not equal x. So since none of these things, this doesn't equal x, this doesn't equal x, and they don't even equal each other, since f of x and g of x are not inverses. Okay. Now, remember I told you when you end a proof, you put this box, and that means end of proof. Okay. Well, there it is. There's another way to end a proof, and that's to write QED. Okay. But I like the bar. I like the little black square better. So that's your conclusion. So now back on number 6, like, what would you write in the answer field? You would write here like C attached work but f of x and g of x are not inverse. Okay? And I know that that's not as, it seems like somehow not as exciting. I mean, look, even on this one, I put an exclamation point. So, yeah, it seems kind of like a letdown, but it's not. We should be agnostic about whether this something is true or false. We're just here to seek out what the truth statement really is. Okay, so we're going to be moving on to a different section when we return. All right, ladies and gentlemen, here we are with number 7, 8, and 9, starting with number 7. Now, what are we asked to do? We are asked to determine the domain and range, and we're asked to state that two different ways, using inequality notation, which I'll show you how to do, and using interval notation, which I will also show you how to do. Let's start with number 7. So I should say, before we begin, domain is x and range is y. That should make it simple enough. So look at number 7. What is the smallest x value? Okay, it begins at -2, and that's an arrowhead, which means it goes up, goes on forever, and it's angled slightly to the right, which means, you know, it's going to keep going on forever in the x direction to infinity. Okay, so let's put our solutions here. I was writing those in red. So first we'll start with our inequality notation. We have, and I'm going to put like domain here and range. I can make it like a table. We'll see how this works out. So inequality notation. This is going to be -2, and then we put a less than symbol because it's an open circle, and then we put an x because we're referring to the domain, and then because it goes on for infinity, we write less than or equal to infinity. Okay, that's the domain. Now let's look at the range. Well, in this case, this is kind of boring because the range is the same. The y value is -2, and it goes up forever. Okay, so the range in inequality notation is -2 with an open circle, so less than y less than or equal to infinity. Okay, and so now interval notation. And I guess the best way to explain this is this symbol corresponds to less than or equal to. All right, this symbol corresponds to less than. I mean, the same thing goes for this. This closing bracket here would mean that that corresponds to like less than or equal to, okay? And the closing parentheses would be that. Okay. Now there's only one case in which this correspondence between the inequality and the interval notation breaks down, and that is when we're doing infinity. So I'll show you. It's just something you have to learn. So let's go back to interval notation. What would be our opening symbol, right? It's going to be one of these two. So in this case, it would be open parentheses -2, meaning that it doesn't include -2. Okay? And then where does it end? So this is like comma. And then where does it end? It ends at infinity. And we close that with a parentheses. Now, I know I just said that in the inequality notation, we use the less than or equal to symbol, but in the interval notation, when it's infinity, we close it with the parentheses. I'll just leave it at that. Okay. And for the range, same deal. Open parentheses, less than or equal to. Open parentheses, -2, comma, infinity, close parentheses. All right. Okay, now let's move on to number 8. Okay, now let's look here at number 8. All right. Let's set up our little table again. So we've got the inequality notation, and then we got the interval notation, and then we've got the domain and the range. Okay, so this one actually is finite, so we can define it. All right, so it's hard to read, but this is -1, 2, 3, 4, 5, 6. That's an open circle. So for the inequality notation domain, the lowest value is -6, less than x, and then we close with a closed circle at 5. So less than or equal to 5. Now range, okay, we need to look at the y values. So here, the lowest y value is -2. You see that? Okay, so the range, the lowest y value is -2. And is it an open circle or a closed circle? Well, over here it's an open circle. So you might be tempted to say less than. But over here it's a closed circle. So you choose the closed circle. And you say, well, it's somewhere it's defined. So that's a less than or equal to. And now up here, we top out at 2. Okay. So we go from -2 to 2. And up here, this solid line indicates that it's going to be less than or equal to. So it's -2 less than or equal to y, less than or equal to 2. Now on to the interval notation for the domain. For the domain. We start at -6. We're looking at the x-axis here. Okay. That's an open circle. Okay. So we're going to do an open parentheses and write -6. Comma, and it goes all the way over to 5, and it's a closed circle. So 5, and then we're going to use the close bracket. This. And that means it includes the 5. Okay? And now on to interval notation for the range. Remember we said that even though this guy here is open, this guy here is closed, we're only concerned that one of them are closed. So in that case, we're going to use an open bracket to indicate that it is defined here at -2 at the low end. And then at the high end, it's also defined. So it's going to be a closing bracket, comma, +2. And we're going to close that bracket like this. Okay? So there's your interval notation and your inequality notation for number 8. And finally, here we move on to our last problem, number 9. And we have room over here, so we'll write this stuff up here. Here we've got our inequality notation. And down here we're going to have our interval notation. And then I've got the domain and the range. First, check for any infinities. Well, there's an arrowhead. So I see that for both my domain and my range, the right side's going to be infinity, okay? Because it's going down into the right, okay? Over here, that's a closed circle. And then, man, this is hard to read. That looks like a -2, and that looks like a -4. I'm going to call it a -4 because I can barely read that. And then up here, this number here, that's a 3. Okay, so we'll see where we get. So for the domain in inequality form, it's a closed circle. So we're going to do -4 on the x-axis. It starts at -4. Less than or equal to x, because x is domain, and then less than or equal to infinity. Okay? Because it goes on forever. And for the range. Now, this really confuses a lot of people. So we remember, we start with the lowest value. What is the lowest value that this will take on? Well, the lowest value is actually -infinity, right? So if you think about the y-axis here, okay, this guy is going down, 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 okay? So its beginning point is -infinity, and its ending point is the highest point it ever gets to, which is 3. So for the range, you're going to write -infinity, less than or equal to y, and then because it's a closed dot at 3, that's the top, you're going to write less than or equal to 3. That's always confusing, especially when the arrow is pointing like that. You're tempted to flip these two, and that would be wrong. Okay, you start with the lowest value, go to the highest value. Same thing for interval notation. So what are we doing here? We're doing bracket -4, comma, infinity, parentheses. All right, and then for the range, this time we're going to do an open parentheses, -infinity, comma, and then this guy tops out at 3, and it's a closed circle, so we put 3 close bracket, like that. Does that make sense? I hope so. All right, well, that takes care of 7, 8, and 9. We're going to move on to the next section where we solve some absolute value equations. That's going to be very exciting. And we'll see you there in the next section. All right, students. So here we are on a new section about absolute value equations. So before we begin doing any of this, we really need to understand the rules about absolute value, because this can either be really easy or insanely difficult. So I don't know about you, but the first part sounds good. So let's go over those rules. here are the rules, okay? Now, I took the formal language and I tried to turn it into language that, like normal humans use. And I kind of distilled it down to 4 rules. I'm sure there's some mathematician somewhere that's smashing their head into a wall saying that I forgot something. But this is basically it. Now, you might want to write these down, okay? Just keep them so you have them on your review, so you can review them and you can look them over and make sure you understand them for the test, etc., 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 blah, blah, blah. Let's look at rule number 1. The solution must be positive. Okay, so the absolute value, right? The absolute value of anything is positive. So, and you can get lost in the problem. It can get so complex that you forget the most basic aspect of this, which is that the answer you end up with must be positive. So, that's where we get to this concept of extraneous solutions. Okay, see this word, extraneous. So note, you will often find 2 possible solutions. Any negative value is considered extraneous, so you can throw it out. Now I need to explain what I mean by that, okay? So you have to plug it in, all right? So I'm going to show you something. You might come up with a solution set that looks like this. You use brackets, and those are really ugly, but you might have a 9 and a -3, okay? Now, you're not sure which one of these is one of these might be the extraneous solution. It's not necessarily that number, okay? That could be the right answer, and this could be the extraneous solution. What you would then have to do is you'd have to go back to your absolute value problem, whatever it is. I'm just making one up, okay? And you'd have to plug in these numbers and see which ones come out to nonsense, okay? And the best way to learn how to check for extraneous solutions is to just do it. So when we get to the problems, I'll show you how to check for extraneous solutions. But basically, you're just plugging in what you get for x back into the original problem and see if it makes sense. Rule number 2, you must isolate the absolute value on the left side before solving. So I gave an example here. Absolute value of blah equals 15, okay? There can't be anything else on the left side. So let's go over and look at the problems real quick, and then we'll come back to the rules. You see over here, we got to get rid of this 3 in the denominator before we can even begin to think about the answer, okay? And over here, we've got to get rid of the 6 and the -3 before we can even begin. Here, we got to get rid of the -2 and the -4, right? We had to isolate the absolute value part. And then on the right side, it's just going to be some number, okay? Or an algebraic expression or whatever. But the absolute value has to be isolated on the left side, okay? So here's an example in 13 and 14 where the absolute value is already isolated and it's set equal to an algebraic expression. That's fine. So actually 13 and 14, there's no preliminary work before we have to begin, okay? And as far as these inequalities go, they're solved kind of the same way as equations. So don't worry too much about inequalities. Let's go back to the rules. Okay, rule number 3. Since you aren't sure whether the original variable was positive or negative, you create a tree. Okay, and I'll show you what I mean by that. And you actually end up solving 2 different equations, setting the number on the right side of the equal sign or the expression. You give it a positive and you give it a negative. Okay, then you, on the left side, you drop the absolute value and you solve. Okay, and that's how you generate those multiple solutions that you put inside the braces. Rule number 4, you cannot distribute into the absolute value. So back to the problems, one thing I'll see a lot of is look at number 11. So what would we do? First, you would subtract 6 from both sides, and then a lot of people I see try to distribute multiply the -3 to the 8 and the -1/2 x, as if those absolute value bars were kind of like parentheses. Well, don't do that. You can't do that. That's not a thing, okay? You can't do that. So no distribution. Okay, what's inside the absolute value must stay there, and it can't be affected by anything outside. It's impervious. It's like it's in a bubble, okay? And with that, I think that concludes kind of like my version of the rules. And again, practice makes perfect. So when we come back, we'll start working on the problems, and all these rules will come into play, and you will understand everything, and I'll explain every step. All right, ladies and gentlemen, here we are with number 10. So solve, and then the way we read it is absolute value of -7 plus 10n over 3 equals 15. Okay, so what would be your opening move here? First of all, I hope you write this down, because you need to rewrite the problem. There's not enough space on the review. Okay, so please take the time, pause the video, write this down so that you actually have room to work it out. Well, what I would do is I would multiply both sides by 3 over 1. Doesn't that make sense? And this time you can just do 3 on the right. That way the 3's cancel over here on the left, and now I've isolated the absolute value, which was one of our rules. So this gives me absolute value -7 plus 10n, absolute value symbol, okay, equals 45. Now here's where I told you in the rules you'll create a tree. Okay, so what do I mean by that? Here's what I mean. You're going to create a tree like this. And here's what you're going to write. You're going to drop these bars. You're going to say -7 plus 10n equals 45. And over here, you're going to say -7 plus 10n equals -45. So the thing that changed signs is this. The thing inside the absolute value, that doesn't change signs. You see how it's plus 10n plus 10. You change the thing on the right. Okay? So now we're going to solve two equations. So this is pretty simple. I'm just going to add 7 to both sides. Okay, so 10n. 45 plus 7 is 52. Okay, and then I guess I would divide by 10. So n equals 52 over 10. Well, that can be reduced by dividing by 2. So what's 52 divided by 2? 2 goes into 5 2 times, 26. So we could write 26/5. Do we agree that that's irreducible? Yeah. Okay. We don't know if that's right or wrong. So now we do the same thing here. Plus 7. Plus 7. Remember, this is a negative. 45 plus 7, so you're really subtracting. And now you have 10n equals, and what's 45 minus 7? 38? Is that right? Yeah, 38 over 7. 38. Okay. And now I guess I would divide by 10. But would it be negative 38? Yep, it would be negative 38. Now I divide by 10. Cancel, cancel. So n equals negative 38 over 10, which can be reduced. So n equals, divide by 2, right? And 38 divided by 2 is 19. So this would be negative 19/5. And so here are your possible answers, okay? So here's how you write that. You do open brace, and then I always list the smallest number first, negative 19 over 5. For some reason, I don't always see it listed this way, but it just makes sense to list the numbers in order from least to greatest, and then 26/5. So these are your possible answers, okay? Now, how do you know if they're correct? Well, you need to plug them in to the problem to check. You got to check and see if either of these pardon me, if either of these creates like a ridiculous answer. Okay, so let's do that. Let's do check 1. All right, so let's check negative 19/5. Okay. Well, what do? Well, I'm just going to plug it in. Absolute value negative 7 plus 10 times negative 19/5. Okay, close parentheses, absolute value, and then that was equal to 45. So the thing is, the left side should equal the right side, right? So when I get through multiplying this all out, the absolute value of whatever I get inside should be 45. If it isn't, then that's an extraneous solution, because it's not the same, okay? It's not an equivalence. Anyway, we got to do the math. So this equals the absolute value of negative 7 plus, and here I can do a little bit of fancy trickery. I can cancel the 5 and the 10 and write a 2 here. Basically divide 10 by 5. And then just multiply the 2 times the negative 19. That gives me negative 38. Sorry, I hope that was clear what I did. I canceled the 10 and the 5, and I wrote a 2 outside, then distributed that to the negative 19, wrote negative 38 right here. Close this off, equals 45. Well, what's negative 7 plus negative 38? Negative plus a negative is a bigger negative, so this is absolute value of negative 45 equals 45. And you should put like a question mark. Is that true? Well, the absolute value of a negative number is just its positive counterpart. So therefore, I love this. Yeah, we get any chance we get to write that symbol is so cool. 45 equals 45. So guess what? That's a valid solution. Now let's check 26/5. Okay, so we have absolute value, negative 7, plus 10, open parentheses, 26/5, close parentheses, absolute value equals 45. Okay, so cancel, cancel. This is a 2. 2 times 26 is 52. So this equals the absolute value of negative 7 plus 52. Absolute value equals 45. Is that true? Well, negative 7 plus 52 is 45. So the absolute value of 45 is 45. We get to use our therefore symbol again. Therefore, yay, 45 equals 45. So do you see what I mean by check? Okay, so that works out too. And what this is, and you should burn this into your brain. This is called the Identity Property of Equality, IPE. Like that's what you're doing, the Identity Property of Equality. So the fact that the thing on the left equals the thing on the right means that your answers are true. Okay, so up here, you both of these are valid solutions. Okay, both are valid. Okay, I was going to do 2 check marks there. Both are valid. So what are we going to write in the answer box for number 10? We're going to write negative 19 over 5 and 26 over 5. Okay. So we're going to put open brace. And we're going to write negative 19 over 5. I was doing this in red. And what did I do? 26 over 5? Yeah. Close brace. And I can make this red. Watch this. Select it, and then hit red. Okay. And that is number 10. All right, ladies and gentlemen, here we are with number 11. So step 1, because I copied and pasted this, step 1 is you're going to rewrite this because you don't have enough space on your review. You've got to have some kind of blank sheet of paper or your notebooks or whatever, and you rewrite it. I'm going to rewrite it too. So let's write 6 minus 3. This vertical bar, absolute value, 8 minus 1/2 x, absolute value bar equals negative 9. Okay, so kind of what's your opening move here? Subtract 6 from both sides? Sounds good. Let's subtract 6 from both sides. I like it. And so then on the left, I'll have negative 3, absolute value, 8 minus 1 over 2x, close the absolute value bar, equals, now negative 9 minus 6 is going to be negative 15. Okay. Well, now what would you do? You can't distribute the negative 3, so you better divide it out. Okay, so let's divide it out. We're going to divide both sides by negative 3. And that allows us to cancel the negative 3's. Yay. Now we've isolated the absolute value, and that's good news. So 8 minus 1 over 2x, absolute value bar, equals negative 15 divided by negative 3 is positive 5. Okay, 5. Positive 5. All right. And here comes your branching tree structure, ladies and gentlemen. Branching tree structure. Remember, we're going to try plus minus, okay? That's what we're going to do. So we're going to set this absolute value equal to positive 5, and then we're going to set it equal to negative 5, and we're going to come up with two different answers. Then we're going to check those answers by plugging them back in to see if the identity property of equality emerges. So, very quickly, let's solve. This is 8 minus 1 over 2x equals positive 5, and then 8 minus 1 over 2x equals negative 5. Okay? We have absolutely no idea which one of these is true. They could both be true. They could both be false. One of them could be true, one of them could be false. Blah, blah, blah. So I'm subtracting 8 from both sides. Now I've got negative 1/2 x equals 5 minus 8 is negative 3. Now what? Multiply both sides by the reciprocal of the x coefficient. Say what? Multiply both sides by negative 2 over 1. Okay? Flip it. So over here I can just multiply by negative 2. And the chief benefit of that is that these cancel. Okay? Leaving behind, the negative cancels that too, right? Leaving behind just the x. So now I have x equals negative 3 times negative 2 equals positive 6. Okay, very good. Now, here, the same thing, minus 8 on both sides. Now I have negative 1/2 x equals negative 13. Okay. Same thing, multiply both sides by the reciprocal of the x coefficient, which means negative 2 over 1. And over here I just can do the negative 2. Blah, blah, blah. Cancel, cancel, including the negative there. Okay, everything cancels. It's all canceled. Just the x. Got the x equals negative 13 times negative 2 is positive 26. So, my set of possible solutions is open brace 6, 26. Close brace. And now we must check. Okay, so we'll check. We'll kind of check up here. Okay, let me find a different color here. Let me do blue. First we'll check. What was it, 6? Check 6. Yeah. So where are we plugging this in? Like, am I plugging it in here? No. Go down here. You're plugging it into this thing. So check 6. Absolute value 8 minus 1 over 2, open parentheses, and then here you're going to put the thing you're checking, which is 6, close the parentheses, close the absolute value, and set it equal to 5. Okay, so whatever we get, the absolute value of that should be 5. I can already tell it's going to work. So we have absolute, this equals absolute value of 8. Now look, if you distribute, multiply, if you think of this as 8 plus, open parentheses, negative 1/2 times 6, this makes more sense, right? Because then you have negative 6 over 2, which is negative 3. So you have 8 minus 3. Okay. Equals 5. Remember, this is kind of a question. It's like, does it? So we have the absolute value of 5 equals 5. Therefore, yay! Therefore, 5 equals 5. How? By the identity property of equality. You know, just to be super nerds, let's put that box there. Like, end of proof, sucker. You know? So we know that 6 is a valid solution. That's basically what we just proved. So 6 is good to go. Now what do we check? 26. Alrighty. Whoa. Now we'll check 26. Okay. I think I'm going to run into some space issues here. But we'll see. I'll just write smaller. Let me check 26. So I have the absolute value of 8 minus 1 over 2, open parentheses, 26, close parentheses, close the absolute value, equals 5. You know, and it's a question, does it? I don't know. This equals absolute value, 8, and then basically negative 1/2 times 26. 26 divided by 2 is 13, so make it negative. So just do 8 minus 13. Close the absolute value. Does it equal 5? So this equals the absolute value of negative 5 equals 5, but the absolute value of any number is positive, so the absolute, therefore, my favorite symbol, 5 equals 5. End of proof. Wait, we can't do that. We have to write y. The identity property of equality. End of proof. Okay. So 26 works. So in this case, both of our solutions were valid. So here, both are valid. Both are valid. Yay. So 6, 26. Embraces. Okay. This is number 11. So open brace 6, 26. Close brace. Try to be neat, okay? And that concludes number 11. All right, students, so here we are on number 12. And what we're being asked to do here is what we've been asked to do for all of the previous absolute value problems, is just find all the true solutions, okay? So I added that, but that's, that's the instructions. So please take the time to write this down, because you need to write it down on a separate sheet of paper, blah, 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 and then we'll begin. Okay, so I'm assuming that you're ready to begin. And what would be our first opening move here? We can't multiply out the negative 2 just yet because we got this negative 4 over here. So step 1, IMHO, would be to add 4 to both sides. Okay, that would get rid of that. And then we would have the absolute value of 6 plus 4k over negative 2 equals, and then negative 2 plus 4 is positive 2. Okay. Now what? Well, multiply both sides by negative 2 over 1. Okay, and here you can just do negative 2. And that cancels the denominator. And we've isolated the absolute value, which is what we wanted to do. So now we can move this over a little bit. Absolute value of 6 plus 4k close the absolute value, equals -4. Okay, so now it's time for branching tree structure. Let's use the cool like colors here. We can do this and this. Okay, so what are our two branching tree structure equations? Well, you've got 6 plus 4k equals -4. And then you've got 6 plus 4k equals -4. See, I just treat it like, I act like a robot, you know? And so, of course, that's going to be +4, right? Because the double negatives make a positive. So basically, it's 6 plus 4k equals 4. But just in case there's somebody who's looking at this that wants to see that intermediate step, that's what's going on. And we will fix that in a second. So let's start with the left one. So what would we do here? I guess I'd subtract 6 from both sides. Let's choose some new color. Blue. -6 and -6. Cancel. Okay, so now I have 4k equals -10. I guess we would divide by 4. Seems like the right thing to do. Come on. Divide both sides by 4. And then reduce the fraction. Cancel, cancel. K equals. Divide the greatest common factor here would be 2. So that would be -5/2. -5/2. Okay, possible solution number 1. Now, we are going to write this out. 6 plus 4k equals +4. I suppose we do the same thing. Subtract 6 from both sides. And then we have 4k equals -2. And then I would divide both sides by 4 and reduce the fraction. K equals, is everybody comfortable with me saying -1/2? Yeah. Okay, so our proposed solutions are, in order from least to greatest, -5/2, comma, -1/2. Question is, are either of those extraneous? So we begin the process of checking. Okay, so let's check. Where can I check? I guess I can check up here. So first I'll check -5/2. So let me check -5/2. And basically I'm just going to plug that in here. Let me do it in black. I've got absolute value of 6 plus 4, and then open parentheses, and we stick that -5/2 in there. -5/2. Close the parentheses. Close the absolute value and set it equal to -4. And this is really like a question, right? Is it? Well, let's keep going. So this equals absolute value 6. And now, before we write the plus, think about what you're doing. You're going to multiply 4 times -5. That's -20. Then you're going to divide by 2, and that's -10. So you write 6 minus 10. Do you feel me? See where this is going? equals negative 4. Okay, so now this, we have 6 minus 10, sorry, we have negative 4. Absolute value of negative 4 equals negative 4. I'm about to reveal something to you. So anyway, the absolute value of a negative number is a positive number. So this is what I'm claiming. I'm claiming that 4 is equal to negative 4. Is that true? This is a false equivalence. So what happened here? Okay, let me show you what happened. And let me show you why I didn't stop this problem early on. So alert, 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 false equivalence. So something is wrong. And what's wrong? Well, let's go back to our rules. Where did they go? Here we go. The solution must be positive. Okay. So what does that mean? That means it might be time to add a little note here. Okay. E.g., that means, like, for example, all right? If you have the absolute value of blob, all right, and that's equal to a negative number, then there is no solution. So if it's all framed up like this, and there's the absolute value bars are the only thing, and the stuff inside the absolute value bar is the only thing on the left, and then on the right side it's a negative number, it's no solution automatically. Okay. The reason I didn't tell you that, well, I did tell you that. I mean, I said in the rule, I said it, rule number 1, the solution must be positive, right? But the reason I made you go through the process on number 12 is because if I just tell you, okay, when you got here to this part of the problem, you should have noticed this. Now, before we just walk away from this, let's make sure that we're right about our conclusion that this is going to be a no solution problem. What do? First, we added 4 to both sides, okay, and we came up with positive 2. Then we multiplied both sides by the denominator, which is negative 2, which made that negative 4. Yep. Now, let me just go back to the original problem, make sure I copied it down correctly, because that could have been an issue. All right, let's see, what would we have done? We would have added 4 to both sides, giving us positive 2, then multiply, yep. So here's what I would write here. I would write no solution. Okay. And the thing is, you have to show work. You can't just make a statement. You have to back it up. And that's what this is. Okay? This is like proof. Like why is this wrong? Well, because when you solve it out, you get a false equivalence. Okay? And we're not going to check the other one, but you get a false equivalence there as well. Okay? So now we find out, now you've learned that you can get a no solution. Okay? So you might want to take a moment and add that. If you wrote down the rules, you might want to add that. That if you isolate the absolute value and the number on the right is a negative, there is no solution. What is going on with the ruler? There's no solution. Okay? So now we are done with number 12. All right, students, so here we are on number 13, and we're asked to find all the true solutions for, that would be all the non-extraneous solutions for the absolute value of x plus 24 equals negative 7x. Now, remember in problem 12, I said if the absolute value was isolated on the left and then on the right there was a negative, you could just write no solution. Well, there's a little caveat to that, which is if on the right side there's a variable, you can't jump to that conclusion. Okay, you can't, because you don't know what the variable is, right? The variable could be a negative number, which would make, it would be multiplied by negative 7, which would make the right side positive. You see where I'm going with this? So you can't jump to conclusions there. So let's go ahead and do this problem. So we've not yet done an absolute value equation where the right side had a variable. So this is going to be unique. Well, it's not much different than what we did before. So we're going to create a branching tree structure because there's nothing to do over here on the right, on the left. We'll create a little branching tree structure. And on the left, I've got x plus 24 equals negative 7x. And then on the right, I've got x plus 24 equals negative 7x. Okay, so that's a double negative. That'll become a positive. Well, let's work on this side. Now, what would I do? I want to get the x's together, and then I want to isolate x by itself. So I want to solve for x on the left. So first things first, remember that there's a 1 in front of this x. So now I'm going to add 7x to both sides. This often confuses students. Over here you've got 8x plus 24, but then on the right, what have you got? You have 0. Okay, so that's okay, right? That's allowed. So this little intermediate step. Now I would subtract 24 from both sides and divide by 8 and get x equals negative 3. Anyway, now we have 8x equals negative 24. And we are going to we are going to divide both sides by 8. And that will cancel, giving me x equals negative 3. Okay. Okay, so that's one possible solution. Now let's go over here. So I've got this double negative, it's going to be a positive. So first line, we're just going to put x plus 24 equals 7x. And remembering that there's a 1 in front of this x, I want to get the x's together, so I want to subtract 7x since I want to solve for x, keeping x on the left. Doesn't really matter, but I prefer it. So subtract 7x from both sides. And on the left, 1 minus 7x gives you negative 6x plus 24. I think you see where this is going. Equals 0. Now I subtract 24 from both sides. And I get negative 6x equals negative 24. And what am I going to do now? I'm going to divide both sides by the coefficient of the x variable, -6. Divide both sides by -6. Cancel those -6. Isolate the x variable. Now, -24 divided by -6 is +4. So here are my two possible solutions. -3 and +4. We should notate that these are the possible solutions. Okay, we have to check them before they become the solutions. All right, so now let's check. Let's check. So let's check -3. Let's check -3. I'm going to just plug it in here. So everywhere I see an x, I'm going to put a -3. So I have the absolute value of -3 plus 24. And I want to see if the absolute value of -3 plus 24, it's the question, right? Is that equal to -7 times -3? Okay, well, let's see. -3 plus 24 is kind of like 24 minus 3, right? So that's 21. So I have the absolute value of 21. And that's equal to -7 times -3, which is +21. Therefore, by the identity property of equality, 21 equals 21. Identity property of equality, close the proof. We're done. We proved it. Okay, so -3 is definitely a solution. So now we'll check the other one. Let's check what we get. 4? Let's check 4. Okay, so I've got the absolute value of 4 plus 24. Ooh, I don't see this going right. You can already see what's wrong. So I got negative... Ooh, maybe not. -7, open parentheses, +4. Okay, this might be a problem. This, right? Because let's see. Well, let's just see what happens. So 4 plus 24, big brain time. That's the absolute value of 28. And that's equal to, ouch, -28. Remember our rule? Okay, there's no variable over here now, so this doesn't work. And because what is the absolute value of 28? It's 28. So 28, ladies and gentlemen, and this is going to be a big revelation, does not equal -28. So what does that mean? That means four is an, here's our key word, extraneous solution. So that's not part of the like final solution set. Yeah, we discard it. Okay, so you discard 4. All right, so let's go back to our solution set, and we don't like you. Okay, so we're not gonna include that. That one got killed out. So our final solution set Let's fix this. So this became the final solution set, which just includes one element, -3. Okay, so that's the answer to number 13. So we're going to go to the worksheet, to number 13. And we are going to write open brace, -3, close brace. And we might write down here in parentheses, 4 was extraneous. I don't know if they want you to put that, it's in the work, right? But there it is, number 13. Okay, so same thing is going to be for number 14. Okay, so let me get that set up, and then you'll just see a jump, and we'll be started on number 14. All right, ladies and gentlemen, here we are, number 14. I went ahead and kind of wrote in some different instructions this time that basically say the same thing. Solve the equation and exclude any extraneous solutions. And I went ahead and added to our rules a little additional rule. We were talking before about the issue of if absolute value of blob equals some negative number, you can automatically say no solution. And then we got to that problem where there was the -7x, and I said, that rule is true except when there is a variable. So I went ahead and added that in. You might want to add this in, unless the right side has a variable, in which case you can't just use this simplistic, automatic, algorithmic no solution, right? You got to actually work it out. But if it's a constant, if it's, -5, -1 billion, you can just immediately say no solution. But if it's -1 billion x, then you have no clue and you have to work it out. All right, back to number 14. Okay, so on the left side, we already have the absolute value all by itself. So it's time for the branching tree structure. But we have on the right side more than one thing. Okay, so what do? Because remember how we do the positive and the negative? Well, what we're going to do is put this in parentheses, okay? And think of it as a single thing, okay? Just think of it as a thing, right? So we're going to try out a positive and a negative version of the thing. That's how I like to look at it. So time for branching tree structure. We're going to need to make this a rather wide branching tree structure. So on the left, I have 4x plus 5 equals the positive version, 2x plus 4. And then over here, my second one is 4x plus 5 equals negative, open parentheses, 2x plus 4. What's going to happen here is we're going to interpret this to be a -1, and you're going to distribute that -1 here. Okay, but we'll get to that. I just wanted to make sure you understand what's going to happen there and how that works. So put in parentheses. You're still going to consider the positive and negative versions of this. So anyway, we're ready to rock and roll on the left. Let's subtract 2x from both sides. So I have 2x plus 5 equals 4. Subtract 5 from both sides. I have 2x equals negative 1. Divide both sides by 2. Cancel, cancel. I have x equals negative 1 over 2. Okay, so that's a possible solution. Moving on. Here, I have 4x plus 5 equals negative 2x minus 4. I'm going to add 2x to both sides. Giving me 6x plus 5 equals negative 4. I'm going to subtract 5 from both sides, giving me 6x equals negative 9. And then I'm going to divide both sides by 6 and reduce the fraction. Of course, the GCF would be 3. X equals negative 3 over 2. So my two possible solutions are both fractions with 2 in the denominator. That's interesting. So here are my possible solutions. The bigger negative number is negative 3 over 2, so I would choose to list that first, then negative 1 over 2. Okay, we're going to check both of them. So now we got to check. Okay, so why don't we check the negative 3 over 2? Let's check. I didn't mean to write those two dots. Let's check negative 3 over 2. There. Okay, so everywhere I see an x, I'm going to put negative 3 over 2. Okay, so I kind of need to keep that in focus. So I'm going to write absolute value for, open parentheses, negative 3 over 2, close parentheses, plus 5, close absolute value, equals 2, open parentheses, negative 3 over 2, close parentheses, plus 4. All right. Okay, now we're ready to rock and roll. Well, one easy thing I can do is cancel here and here, leaving a 2. 2 times negative 3 is negative 6. Negative 6 plus 5 is negative 1. Okay, let me make sure we did all that right. So I canceled the 4 and the 2. Like 2 times negative 3 is negative 6. So we'll go ahead and write that intermediate step. We agree that it's negative 6 plus 5. Absolute value equals, these twos cancel. So then I have negative 3 plus 4. Okay. What's negative 6 plus 5? Negative 1. So I have the absolute value of negative 1, which is going to be 1. And then negative 3 plus 4 equals 1. So therefore, 1 equals 1 by the identity property of equality. End of proof. Okay, so that solution works out. -3/2. Well, now we better check -1/2. So let's check it out. We have, so now what are we doing? We are checking -1/2. So I have the absolute value of 4, open parentheses, -1/2, close parentheses, plus 5, close absolute value, equals 2, open parentheses, -1/2, close parentheses, plus 4. And now we are ready to figure this out. So just like before, I'm going to cancel, leaving behind a 2. 2 times -1 is -2. -2 plus 5 is 3. So anyway, we'll go ahead and show all that intermediate work. We do agree, though, about this cancellation. So 2 times -1 is -2. So I'm going to go ahead and write absolute value -2 plus 5. Absolute value equals, cancel, I have -1 plus 4. Why did I write a 3? Because my brain was working ahead, right? That's what -1 plus 4 is. All right, so now I have -2 plus 5 equals 3. So I've got the absolute value of 3 equals 3. Therefore, 3 equals 3 by the identity property of equality. End of proof. Okay, so that one worked out as well. So in this case, both of our solutions worked. So those are no longer possible solutions, right? These are now verified solutions, or proven. Okay, so we're good to go. So we're going to write both of those down, -3/2, -1/2, as our answer. -3/2, -1/2. So I've got -3/2, -1/2. Let me close off the braces there, and we conclude number 14. Looking ahead, we jump into inequalities, which they want us to graph the inequalities. Okay, so basically we're solving absolute value functions. Equations. We're going to have to talk about when to flip the sign, flip the inequality sign, and then what happens. Determine the domain and range of the inverse. Okay, well, write your answers as inequalities and interval. We already did that. So just on number 19, what we're going to do is just plot out some points. We're going to find some places where the graph hits one of these dots, and then figure out what the coordinates are and just reverse the x and the y values, and then we'll figure it out. Wait, hold on. I think I'm overthinking that. No. We're going to have to do that, and then we'll go ahead and plot it. Actually, we only need to do it for three points. This one, and this one. We don't even need to graph it. It doesn't say graph it. Blah, blah, blah. We'll get to that. That's going to be easy. What else is there? That's it? Okay. So we just have the inequalities and then the domain and range problem. That's going to be super easy. The inequalities are going to be a little quirky, so we'll come to those in just a moment. All right, ladies and gentlemen, before we can begin solving and graphing absolute value inequalities, we must take a brief moment and take some notes, because there are rules. You can't just jump into it. You have to understand what you're doing. And so I'm going to go through this methodically with you. You should write everything you see here down. And then just follow my examples that I show, to the letter, right? So there's kind of two parts to this. First, the solving part, and then the graphing part. So let's just see what it says here. When solving absolute value inequalities, you follow essentially the same process as with absolute value equations. But when you make your little tree, your branching tree, you actually flip the inequality symbol and you change the sign of the stuff that's on the right. Okay? So you just add in that flipping of the inequality symbol. And then what you're going to find, instead of getting two different answers or like solutions, you're going to get two different inequalities. And that's what we call a compound inequality, where you have more than one inequality. So once you get that, for now we're just going to assume that they're valid. We're not going to error check them, right? We're just going to assume they're valid. We're going to graph them, okay? Now, this is where writing down the notes is really crucial. So first we take a look at if the original absolute value, like when you get it set up, if the original absolute value is the greater than symbol or greater than or equal to symbol, we use the word or, okay? And but by the way, so what I'm referring to here is the point at which the when you've got the absolute value ready to go, we use the word or. And when we think about it, the word or, we're thinking about it, the logical union symbol. And I'm going to show you what union means. It's a very confusing term, since it's referring to the combination of two things that don't overlap. Okay? So essentially, if this original absolute value inequality has the greater than symbol or greater than or equal to symbol, the graph of the union of those compound inequalities, one of them will go off into negative infinity, the other one will go off into positive infinity, and they won't overlap anywhere. Okay? So we have to, in addition to just drawing that on a graph, we're going to use the interval notation, right? That would be the brackets and the parentheses, to show what's going on in addition to graphing it. Okay? So now, what if the original absolute value inequality symbol has less than or equal to? So in this case, we call this and, okay? And this represents the intersection of the compound inequalities. And you see this upside down U? That upside down U symbol means intersection, or and, or the overlapping region of the two graphed inequalities. So those compound inequalities are going to overlap one another, and the part that we care about is the part where they overlap. We don't care about the part where they don't overlap. So the graph of the intersection will overlap. So we are looking for the part where both inequalities intersect. So we'll also use interval notation to show that intersection as well. Now I've drawn a kind of a Venn diagram here. And the blue part in the middle is the intersection of the two circles, right? So that's the and part. And the light blue parts are where they don't intersect. And that's the or part. That's the union. So you've got the dark blue intersection and you've got the light blue union or. Okay, so this is kind of a picture of the logic. Now scroll down a little bit more. I've got this kind of defined. So for the light blue, we have this U symbol, which means or. It's the point where these don't overlap. And then I give the reference again. If the original inequality symbol is greater than or equal to, this is what you're going to be dealing with. Okay. And then that dark blue region in the middle where they do overlap, we call that and we use this upside down U. And this is the intersection of the two inequalities where they do overlap. And that would be indicated by the original absolute value inequality symbol was less than or equal to. Okay, so I would very carefully, I would draw everything you saw here. I would write it all down. I might back the video up and watch this again. Okay, so you understand the rules. Once you understand the rules, it's fun to play the game. But if you don't understand the rules, everything we do will seem arbitrary and incomprehensible. So please take the time to review this section carefully, okay? Because I want you to understand the logic about what's going on, because it can get tricky. Once you get it, though, it's very simple. It's just you have to mentally overcome this hurdle, especially if you're not familiar with these logical operators, the union symbol and the intersection symbol. And they can be confusing, or and, but I think this picture kind of makes it really clear. Dark blue, and. Light blue, or. Dark blue, intersection. Light blue, union. Dark blue overlaps. Light blue doesn't overlap. Okay? All right. Well, that is going to do it for the rules regarding solving and graphing absolute value inequalities. And when we return, we'll actually put this into practice. All right, ladies and gentlemen, so here we are on number 15, where we're solving and graphing absolute value inequalities. Now, it is mandatory that before you attempt number 15 or any of these absolute value inequalities, that you watch the preceding section of the video where I go over the rules. Without those rules in your mind, everything that I do here will seem utterly confusing. So you need to go back and watch that if you haven't already. And if you did watch it already, I would recommend watching it again. Because now we're going to go ahead and put them into practice. Okay, so first we have to understand something. We're going to isolate the absolute value part of this inequality on the left side. And during that process, we may be flipping the inequality symbol because inequality rules more generally still apply. So remember what those are. This goes back to 7th grade. If you multiply or divide by a negative number, you have to flip the inequality sign. So it's only when we get to the part where we just have the absolute value on the left, whatever the inequality symbol is at that point, that's when we apply those rules, okay? So we don't know what rule yet we're going to apply just by looking at this, because we haven't isolated anything. So let's go ahead and do the problem. So the first thing I'm going to do is add 8 to both sides, and that won't affect anything with the inequality symbol. Only multiplication and division by negative numbers affect the flipping of that. So first things first, add 8 to both sides. So now here I've got 4 absolute value 4x minus 2 absolute value sign greater than or equal to, and now negative 72 plus 8 is like subtraction, so the answer is going to be negative 64. Okay. And now we're going to divide by the positive number 4. So that's not going to mess with the inequality symbol. So we're going to divide both sides by 4. And that cancels the 4, so I have isolated the absolute value on the left, absolute value 4x minus 2, absolute value greater than or equal to, and then negative 64 divided by 4. Let's see. 4 goes into 6 one time, leaving 2 as a remainder. Okay, so negative 1. And then 4 goes into 24 6 times, leaving no remainder. So it's negative 16. Okay, so now we're ready for the branching tree structure, and we already, now that we know what our absolute value inequality symbol is, we can go back and refer to our rules to see which one of these we're going to be dealing with. And we see right away that the symbol is greater than or equal to, so we're going to be dealing with the first scenario here. So let's review that. We have the greater than or equal to symbol. We're going to use the word or. This is going to be the union. So the resulting compound inequalities will not overlap. Okay? We'll use interval notation to show that they go off into infinity and they don't overlap when we graph the compound inequalities. So that would be the light blue region of this Venn diagram. Okay? This is the union of these two inequalities. They don't overlap. Okay, this is the or. All right, so going back, we split them off into our branching tree structure. And remember, when we do this, we're going to change the sign of the whatever's on the right, but we're also going to flip the inequality symbol. Okay. So our first situation is for x minus 2 greater than or equal to negative 16. Our second situation is for x minus 2. We flip the inequality symbol to be less than or equal to, and then we negate whatever's there. So in this case, it's negative 16. Okay? So I'll give you a chance to get all that written down. All right, so let's solve these two inequalities. And the first step on the left side here is going to be to add 2 to both sides. And that's going to give us 4x greater than or equal to negative 14. And we will divide both sides by 4. cancel out the 4's, so we have x. We never multiplied or divided by a negative number, so we didn't flip the sign, so it's just going to be greater than or equal to. And then negative 14 over 4, common factor is 2, so we can write negative 7 over 2. Since we're going to be graphing this, it's useful to write it in decimal form. So 2 goes into 7 3 times, so it's negative 6.5, right? You divide 7 by 2, you get 3 with a remainder of 1 over 2. So it's negative, I didn't mean 6.5, I meant negative 3.5, right? So x is greater than or equal to negative 3.5. Okay? So just to go ahead and kind of preemptively show what that inequality will look like, you have to think about this. So x is any value that's greater than or equal to negative 3.5. So since it's greater than or equal to, the lowest number here in the interval notation will be negative 3.5. Right? And then since it's unbounded, it goes off into infinity forever and ever to positive infinity. And remember, we conclude that with the closing parentheses. Now, this will be a union, a non-overlapping union with whatever we get over here on the next inequality. So let's move over here. And let's take this slowly, step by step, so we don't confuse anyone or lose anyone. So we have 4x minus 2 less than or equal to negative 16. So that's positive 16. In this case, I'm going to add 2 to both sides. Okay, just like before. And I have 4x less than or equal to 18. And I will now divide both sides by 4. Okay, I'm not dividing or multiplying by a negative number, so I'm not going to change that inequality symbol. It will remain less than or equal to. Cancel, cancel. So x is going to be less than or equal to. And here the common factor is also 2. So that's going to be 9 halves. 9 over 2. Now, you have to think about it in decimal form. 2 goes into 9 4 times. 4 times 2 is 8. So it's 8.5, right? So x is less than or equal to 8.5. So the interval notation here is going to be the smallest value that x will be negative infinity, okay? Because x is less than 8.5. So you go here and you put open parentheses negative infinity, comma, and then 8.5 is the highest value that this takes on, right? And you're going to bracket that because it's the less than or equal to symbol. Okay, so what we're looking at here is the union of these two. All right? So we have negative 3.5 going off into positive infinity, and then we have 8.5 going off into negative infinity. Okay, so now we're going to graph this union here, okay? Now remember, we're not interested in the overlapping region. I think it's always very important to go back to the visual. We're interested in the light blue region here. So we're interested in where they don't overlap. Okay, so let's go back. Since this is a union, an OR, a non-overlapping compound inequality graph, let's take a ruler. The graph they provide in the problem is just too small. And let's create a number line going off into infinity in both directions. And we'll put, we'll make this 0. Okay, so this can be, yeah, this will be like 1, 2, 3, 4, 5, 6, 7, 8, 9. That way we can graph that first one there. And then here we just go down, try to keep the same distance, -1, -2, -3, -4, -5, -6, -7. Okay. So let's go ahead and graph this first inequality. And so it starts at -3.5. So I don't know, we'll use green here for this one. So -3.5, this is -1, -2, -3. So -3.5 would be right here. And so what I want to show is, I want to show that this runs off into positive infinity. So let me just show that like this. This is the first inequality. Now the second inequality runs off into negative infinity, and it starts at 8.5. So this is -3.5 here, -7/2. Okay, the second inequality, its highest value, and I should say this is a closed-in circle because it's inclusive. The highest value, let's choose a contrasting color, I don't know, pink. This will be the pink. Or at 8.5, so 1, 2, 3, 4, 5, 6, 7, 8. Right in here, we'll have a closed-in circle to indicate that it's included, and this will be 8.5. And this is x is less than or equal to 8.5. So that what that means is that this graph will go from negative infinity all the way up to 8.5 and then stop. Okay, so let's draw that, and I'll show you what I mean by non-overlapping when we write the final answer. So this guy goes here, and he goes off into negative infinity, like that. Okay, so what we're interested in here is not the part in the middle where they overlap. We're only interested in the part where they don't overlap. All right, so let me find a way to highlight that. What are we interested in? Let me use a color that we haven't used yet. I guess yellow, no, purple. Let's do purple. Okay, so what I'm interested in here, let me make this huge. I'm interested in this region. Okay, going on forever into negative infinity. Okay, that's a negative infinity. Up to -3.5, right? And then I'm interested also in this region, beginning at 8.5 and going off into positive infinity. Okay, so 8.5 and to positive infinity. So let's think about this for a minute. What are we going to write? What would be our what would be the graph that we draw in the end? I want to leave this graph here, okay? But I want to make a copy of it so you can see. This is kind of like sketch work. This is a step that you have to do before you can finalize your graph, because you're going to need to get rid of this part where they appear to overlap, because you're not interested in that part. So I just need to somehow copy this. Maybe like this. No, the memory is going to die on me. Okay, so let me make a copy of it and I'll be right back. Okay, so notice that I've made an exact duplicate of the graph, and what I want to do is I want to get rid of a lot of this stuff, okay? Because now I know what I'm doing. We've kind of mapped out what we're trying to accomplish here, so we can get rid of the majority of the garbage that's written on here. So now we can graph. So what we're interested in is just these parts here. Okay, so let's take a look. Let me take the green, make it a little bigger. So I'm interested in this region here, going off into negative infinity. And I'm interested in this pink region here. In other words, if you'll remember that diagram, that Venn diagram, the circular diagram there that overlapped, I'm interested in the non-overlapping region, which would be these two regions here. Okay, so once again, it's kind of helpful to take this final graph, which is what you would actually draw. This right here is a preliminary graph to kind of help you get your bearings. This is your final graph down here, and it's really helpful to write the interval notation. So this is the interval notation for this absolute value inequality solution here. Because you have a compound inequality, it's useful to write the interval notation. Okay, so just looking at this for a moment, what do you see? You see negative infinity going up to 3.5. Okay, so we have negative infinity. And we bound that with a parentheses. And that is going up to negative 3.5. Okay. And we close that with a bracket because it's a closed-in circle. And then we put the union symbol. Remember, this means or union. And now we're going to look here and we see 8.5 going off into infinity. So we have an open bracket because it's a closed-in dot, 8.5 going off into positive infinity. And we bound that with a closing parentheses. So here's your compound inequality graphed for this absolute value inequality. This is like the complete solution to number 15. Okay, this is one of the reasons why there's definitely not enough space on the page on the actual review to write all that out. And if you notice, you have to go through the preliminary step before you can actually see what the final interval looks like. Because this was a union, we ignore this middle part. Had this been an intersection, we would have ignored the purple part and only focused on the middle part there. Okay? So that's the end of number 15. Okay, students, so here we are with number 16. This is another absolute value inequality. Before we dive into this, I realized that you need something to write down for number 15. So I made this. Take a moment, pause the video, and write down, copy this down. This is what I would include in the solution if I had to include something. Okay. I'm just giving some time here. You might want to press pause because I'm about to just move on. Okay, now I'm going to move on to number 16. And I've got that written down already. So let's move down to where I've got this written down because we clearly don't have enough space to do anything there. So here's number 16. Now, once again, if you haven't already done so, please review the notes on how to solve and graph absolute value inequalities and write that interval notation. And we'll refer to those notes as we go through this problem. So the first step is to just isolate the absolute value by itself. If we find ourselves dividing or multiplying by a negative number, we will flip the sign, so we don't yet know what the final symbol will be. So let's just start by working out the problem. First, I would add 1 to both sides. Okay, and that would leave me on the left with -8, absolute value -p plus 8, absolute value less than or equal to -24. Now I'm going to divide both sides by a negative number, so I will flip this absolute value symbol. So I'm going to divide both sides by -8. And in doing so, I'll have to flip the absolute value sign. So now on the left, I've isolated the absolute value -p plus 8. Flip the absolute value, or flip the inequality symbol from less than or equal to greater than or equal to. And then -24 divided by -8 is +3. So what we're looking at here is a greater than or equal to symbol. So let's go to our notes on this, and we have a greater than or equal to symbol. So this is going to be another union problem where what we're looking for is the non-overlapping region. So this would be, in this Venn diagram, the light blue region. And let's review that notation. The union, which is that big U, is the OR. It's where they don't overlap. Okay? So remember, what we're going to do now is the branching tree structure. And when we do that branching tree structure, the first branch of the tree will just be -p plus 8 greater than or equal to 3. But the second branch will flip the absolute value, or rather the inequality symbol, and change the sign of 3. So let's draw that. Here's that branching tree here. So we've got these two different inequalities. So we drop the absolute value signs and we just draw negative p plus 8 greater than or equal to 3. And here's our compound inequality. We're going to write negative p plus 8. The inequality symbol here has to be flipped, less than or equal to. Now also negate what's on the right, so that would be negative 3. So now we're just going to solve both of these. First thing I'm going to do is subtract 8 from both sides. Okay, and now I have negative p, which I'm going to write as negative 1p for clarity, greater than or equal to 3 minus 8 is negative 5. And what I'll have to do now is divide both sides by the negative 1, and that will flip the inequality symbol yet again. So divide by negative 1 on both sides, and we have p is less than or equal to positive 5. Over here, we subtract 8 from both sides. Okay, and we have negative 1p is less than or equal to negative 11. Once again, I'm going to be dividing by a negative, so I'll have to flip the inequality symbol. Divide by negative 1, divide by negative 1. Okay, these will cancel, and I'll have p, flip the inequality symbol, greater than or equal to positive 11. Okay, so remember this is a union problem, so we're looking for the non-overlapping regions. So we're going to draw a number line here, which is going to be like a preliminary number line, where we'll kind of sketch out what we're going to do. Okay. Let's see what's going on here. So look here, we've got p is less than or equal to 5. So we'll use, I think we used green last time, so we'll stick with that. This will be green. Because this is a less than or equal to symbol, I guess we should demarcate this a little bit. What am I going to do? Since they're both positive, I'll start 0 over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so the important points will be 1, 2, 3, 4, 5 right here. This is 5. And then 6, 7, 8, 9, 10, 11. Here's 11. Okay, so let's go back to the green. We're going to have a closed-in dot right here. And then what's going on is it says it is less than 5, or less than or equal to 5. So what I'm going to draw, this again is the preliminary graph. Okay, this thing goes off into negative infinity. Okay, and then the second graph, or the second inequality is plotted as p is greater than or equal to 11. So in this case, we don't even have to worry about any overlapping parts. We'll just put a closed-in dot here at 11. And then this goes up and to the right, like this. To positive infinity. Okay, so actually this is a, maybe we don't have to draw the second graph, right? we know what's going to happen here. The points that we're interested in are, or the region that we're interested in, or the region that does not overlap. So that would be this region here, going off into negative infinity, and then this region here going to positive infinity. So how would we demarcate this or denote this using interval notation? What we would say is, we would say we have an interval here from negative infinity, and there's a couple ways of writing this. It could just be comma 5 and then close bracket. You could also say negative infinity less than or equal to 5, right? But then that kind of is a redundant statement, since you're kind of combining the inequality notation with the interval notation. Yeah, anyway, the point is made. And then there's that union symbol, okay, in both cases. And then the second thing, we have it starting at bracket 11, going off into positive infinity, and we close that with parentheses. And I guess if you were writing it the other way, you would put bracket 11 is less than or equal to infinity, and you would close the parentheses. So in this case, the preliminary graph is sufficient. We can just go up and write down P is less than or equal to 5 and P is greater than or equal to 11. So we have P is less than or equal to 5, and we should say or P is greater than or equal to 11, and then we use that interval notation that goes from negative infinity to 5, bracket union, open bracket 11, comma positive infinity, close that off. And then what you'd want to do is just, I don't know, you pick a point here. This is going to be 5, right? And we show that that's a closed-end dot. We show this graph goes here to negative infinity, and then here we have a closed-end dot at 11. This is not to scale, going off into positive infinity. That's how I would write the answer to number 16. Okay, well, I think we can just continue now that we have the idea. Okay, so let's take a look at number 17. Number 17 is going to present us with a fun change of pace, because thus far with these absolute value inequalities, we've had unions where we're looking for non-overlapping regions. But here, first of all, we have open circles because we've got that greater than symbol. Now, it might not end up being a greater than symbol. In fact, I can tell just by looking at this problem that it's going to flip. But the cool part is there's going to be open circles, and it might be an intersection instead of a union. So take a moment, and I've got this problem set up down here. Take a moment and write this down in your scratch paper where you're going to write your solutions out, because there's clearly not enough space to do any of our work up there in the actual review. That's just where we're going to put the answers. Okay, I'm just giving a little bit of time, and you can of course pause the video, so I'm just going to continue, and at this point assume that you've written all this down. Okay, so first we have to isolate the absolute value. And to do that, we have to divide by -3, which will cause us to flip that inequality symbol. So let's begin by dividing both sides by -3. Okay. So I'm going to divide the left side by -3 and the right side by -3. Don't forget to flip that inequality symbol. Cancel, cancel. So on the left, I have the absolute value of 4 minus 1/2 x close absolute value. Now flip the inequality symbol. And then -24 divided by -3 is +8. Okay, so at this point we have the branching tree structure. But first, let's analyze. We've got a less than symbol. So let's go over to our notes on graphing absolute value inequalities. And we see that, yay, we get to use this intersection. So in this case, what we're looking for is the region that overlaps, the dark blue. And that's going to be fun. So that's something we haven't done yet. And let's kind of review the notes here. So we have a less than symbol. This is the and situation, which we refer to as the intersection using that symbol that looks like an upside down U, which means intersection. Okay, so the graph of the intersection will overlap. So we're looking for the part where both inequalities intersect. We will also use interval notation to show the intersection. And just to review, we're looking for the dark blue region where the compound inequalities overlap one another. And then I've got just another quick review of that symbol. That upside down U is the and or intersection operator where they do overlap. And that's associated with the less than or equal to symbol. So now that we've kind of reviewed the part of the notes that are pertinent to this problem, let's get back to the problem. So we're going to create the branching tree structure. Okay, and remember that first branch, we're not going to change anything. We're just going to write 4 minus 1/2 x less than 8. But that second branch, we're going to not only flip the inequality symbol to make it a greater than symbol, but we're going to change the sign of 8 to be negative. Okay, so let's start with the left one where we don't do anything. Just drop those absolute value signs and write 4 minus 1/2 x less than 8. Over here, we're going to write 4 minus 1/2 x and we're going to flip the inequality symbol, make it greater than, and we're going to change the sign of 8 to be negative. Okay. All right, so if you've gotten this far, you're probably going to get the rest of it correct. Now all we have to do is isolate x for both of these inequalities. So I'll start by subtracting 4 from both sides, and that doesn't do anything to the inequality symbol since it's just a subtraction. Only multiplication and division by negative numbers flips the inequality symbol, which we're going to do here in a second. So I have negative 1/2 x less than 4. And to isolate the x, I will multiply by the reciprocal of negative 1/2, which we call the coefficient of the x variable, and that would be negative 2 over 1. I'm going to do that on both sides, but over here I can just write negative 2, right? This cancels here, and I have x. Remember to flip the inequality symbol because you multiplied by a negative. So I have x is greater than negative 8. Now let's move over here. First things first, let's subtract 4. Nothing happens to the inequality symbol just yet. Now I've got negative 1/2 x greater than negative 8 minus 4. Now, negative 8 minus 4 gives us negative 12, because we have two negatives, so they become more negative. Now, we are going to multiply by the reciprocal of the x coefficient, which would be negative 2 over 1. On this side, we'll just multiply by negative 2. And the benefit there is all this cancels. And now I have x. Remember to flip the inequality. X is less than negative 12 times 2. Negative 12 times a negative 2 is positive 24. So when I'm creating my graph, I have to create a pretty big graph. It has to span from negative 8 all the way to 24. So I'm going to pause the video and draw that, and then I'll give you a chance to draw it, but I don't want to drag the video out by watching me laboriously creating this number line. Okay, so take a moment to draw the graph or draw the number line. Remember, we're going to be using open circles here for both of these. So I'll use green for the first one. Pause the video, take your time, draw the number line. I would really like you to draw it to scale, but you got to do you, right? So what we're going to do here, let's read this. X is all values greater than but not including negative 8. So we put an open circle here at negative 8. Okay, and now I'm going to this is going to be my preliminary graph. So this guy is going to go all the way here forever and ever to infinity. Okay. Now what's happening with the second inequality? I have x is less than 24. So x begins at negative infinity and it goes all the way up to 24, but it doesn't include 24. Okay, so we'll use the orange and we'll put an open circle here at 24. And to indicate this, sort of move to negative infinity, we'll go up. And then draw this arrow going to the left forever and ever to negative infinity. Okay, so remember, in this case, we're talking about the intersection. This is the and. So we're looking at where these graphs overlap one another. That's the only area we're interested in, the dark blue region of the Venn diagram here. Okay, so the upside down U, the and. Okay, so the region that I'm interested in for my final graph that I draw is going to be this region here, between but not including 24 all the way down to negative 8, but not including negative 8. Like that. So that shaded region is the region that I'm interested in, or that we are interested in. So I'm going to pause the video again and draw another number line so I can show what this should look like in its final form. And then we'll write the interval notation. Okay, so now we're actually going to kind of plot the solution. It's going to be all numbers between but not including negative 8 and 24. Okay, so let's take our ruler and slide it up here, and I'll take the red marker here and make it a little bit bigger. even bigger. Okay, it's this whole region here. There, that kind of gets it. So that's the region we're interested in. So how do we notate this using interval notation? Well, we have an open circle at -8 at the low end, so we would use an open parentheses, and we would write -8. I was writing what that's going to, so first I have -8, and that is going to infinity. Okay, so watch, you can write that, that's okay, so go ahead and write it like that, but now write this symbol, which is indicating that we're looking at the intersection of these two intervals, and we don't care that it goes to infinity because of this. So for this one, we do an open parentheses, and we start at -infinity, and that goes to 24, but because it doesn't include 24, we terminate that with a parentheses. So it kind of looks like you're saying, well, why are we writing the infinity symbols? It doesn't matter, because this notation tells us that we're looking for the intersection only. And that's the beauty of that logical operator. It tells us what to look for, even if we didn't have the picture. Okay. So we're going to include that in our solution. We're also going to include x is greater than -8 and x is less than 24. So let's head up into our problem and actually write this all down in the problem area. Okay, so here I've written down for number 17 everything that you need to draw. Obviously the number line is not to scale, but you've got the work to back it up. So we've written down all the stuff they want. X is greater than -8 and x is less than 24. The and is the dead giveaway. That is directly correlated to the symbol beneath it, which is the intersection operator, or the and operator. And then we use interval notation to show that we have -8 to infinity intersecting with -infinity to 24. And that's everything that you would write for number 17. So great job. I really hope you're starting to get the hang of this. All right, students, so here we are at, unfortunately, because it's actually intellectually stimulating, the final absolute value inequality. I really hope you found this portion of the review interesting. I certainly did. The rest of it's kind of simplistic. This was actually interesting. So let's dig into number 18. So we have no idea what we'll end up with, but I noticed that first I'm going to add 9 to both sides and then multiply by -3, which will flip that sign. And so we'll see what that gives us. Of course, we're going to take a moment here and go down into our work and just rewrite all that. And that is already done for us here. Okay, so take a moment and pause the video and write all of this down. Just copy this all down so that we can work. Okay, I'll assume that you got that done. Now, right away, before we can do anything with that -3, we have to move gotta get the 9 moved. So I'm going to start by adding 9 to both sides, which won't affect the inequality symbol at all. Okay, but just carefully rewrite this. Don't drop any negatives. So this is absolute value negative 2a plus 3, absolute value symbol, fraction bar, negative 3. And we haven't changed the symbol just yet, so it's still less than or equal to. Now, negative 6 plus 9 is the same thing as 9 minus 6, so we should just have positive 3. Okay, now to get rid of the denominator, we are going to be multiplying by negative 3 over 1 on the left, and on the right it's just negative 3. This is going to flip the inequality symbol. Okay, so that gets rid of this. And so let's write this again. We've isolated the absolute value, which is great news. We have negative 2a plus 3. Absolute value of negative 2a plus 3. Flip the sign. Greater than or equal to. 3 times negative 3 is a negative 9. Okay, so before we go any further, we have a greater than or equal to symbol. What are we dealing with? We're dealing with a union here, okay? So the greater than or equal to symbol tells us that we're looking for the non-overlapping regions. We go down here, that's the light blue. We're looking for where they don't intersect. This is union. This is the or, where they don't overlap. Okay? So let's go read the rules just so we make sure we're not messing up. Okay? The graph of the union will go off into infinity in both directions and will not overlap. So we will include interval notation. And we're going to use that the U symbol for union or, okay? Again, it's worth the time to notice this Venn diagram. This is a wonderful image that shows what we're looking for is the light blue colored area. Those areas where they don't intersect or they don't overlap. Union or don't overlap. Okay? So now let's get back to the problem. And we're going to create that branching tree structure. Okay. And let's recall that the first branch or the left branch of the tree is just going to be negative 2a plus 3 greater than or equal to negative 9. The right branch of the tree will be negative 2a plus 3 less than or equal to negative 9 or positive 9. Okay, so we're going to flip the inequality symbol and negate the thing on the right. So let's start on the left. Negative 2a plus 3 greater than or equal to negative 9. And then here we have negative 2a plus 3 less than or equal to negative 9. And I show this intermediate step so you remember that we negate whatever it is, even if that negation is of a negative. So we're negating a negative, which will make that a positive, but we'll get to that in a second. We'll focus in here. So before I can do anything with the negative 2a, I've got to subtract 3 from both sides. It doesn't do anything to the inequality symbol. So I've got negative 2a is greater than or equal to, and now this is addition, negative 9 minus 3 is negative 12. Okay, so now I'm going to divide both sides by negative 2. So I'm dividing by a negative number, which means I'm going to flip the inequality symbol. Divide negative 2, divide negative 2. That cancels out here, leaving a by itself. Flip the inequality symbol. A is now less than the quotient of negative 12 and negative 2, which is positive 6. So a is less than 6, less than or equal to 6. Let's go over and check this one out. So step 1 is to just write negative 2a plus 3 less than or equal to, and now we have that double negative, so it's just positive 9. Now we're going to subtract 3 from both sides, and we have negative 2a less than or equal to positive 6. And now what we're going to do is divide both sides by negative 2, flipping the inequality symbol in the process. So I'm going to divide by negative 2 here and negative 2 here. Cancel, cancel. A flip symbol is now greater than or equal to the quotient of 6 and negative 2, which is negative 3. All right, so let's look at what we have. We've got the union, that is, the non-overlapping regions, depicted by a is less than or equal to 6. So that would mean the highest value that a ever achieves here is 6, and it's less than or equal to 6, so it's going to be a closed-in circle. And then it's going to go down to negative infinity. And then we've also got a is greater than or equal to negative 3. So starting at negative 3, that would be the lowest value that it has, and then it's going to go off to positive infinity. So we're going to see an overlapping region, but we're going to ignore it, right? We're going to ignore it and only look at those two regions that don't overlap. Okay, so let's take a moment to draw our number line and label it out. I'll pause the video here and get that done, so there'll be a flash and then you'll see the number line drawn, and you should draw one as well. Okay, so something like this. This will be our number line here, and we'll start with our green. Now this is going to be a closed-in dot. Now look at what it says. A is less than or equal to 6. So we're going to put a closed-in dot on 6, and then we're going to indicate that this goes into negative infinity territory because it's any number less than or equal to 6. So this will go this way forever to negative infinity. Okay, and for the second one, we'll use orange. And this is at negative 3. Again, it's a closed-in dot. And we want to indicate that that goes, because it says a is greater than or equal to negative 3, it means that it takes on all values of a, all numbers greater than or equal to negative 3. So this goes this way forever to positive infinity. And remember, we're not looking at the intersection of these 2 points. We're looking at the union, or the disjunction, or the area where they don't overlap. Okay, so those two regions are starting at and including negative 3 here, off into negative infinity, and then starting and including 6 to the right, off to positive infinity, completely ignoring the middle part. Okay, so let's take a moment. You're going to hear you're going to see just kind of flash, and we're going to draw another number line where we're going to plot the final solution and then write out the interval notation, and then we'll be done with number 18. Okay, so This is all we need. And what we're going to show in our final solution is this. We're going to show that this orange region goes off. Let's make this bigger. Bigger like this. This orange region goes off into negative infinity territory. Like that. And then we want to show that 6 goes to positive infinity. It's a little big. Let's be consistent. Okay. So this goes off to positive infinity. Just want to make sure this is really obvious that that's a closed-in dot there and a closed-in dot there at negative 3. Okay. So how do we indicate this in interval notation? Well, let's think about it. So for the orange, we have negative infinity up to and including negative 3. So I've got open parentheses, negative infinity up to negative 3 bracket, right, because it's inclusive. Union, right, because we're not looking for the intersection, we're looking for the union, the non-overlapping regions, the light blue colored areas of that Venn diagram. And now I'm going to put a bracket like this to indicate that 6 is part of it. And it goes off to positive infinity, which we terminate with in parentheses. So there's your interval notation there with the union symbol in the middle. And let's remember that this means union or, right? And we're talking about the non-overlapping region. Okay, good. So what do we need to include in our final answer? We need to include A is less than or equal to 6, A is greater than or equal to negative 3, and then this interval notation and the number line. Okay, so we're going to flash back up into the worksheet and we'll show what you actually have to write. Okay, and here we are. So this is it. This is number 18. So this is what I would show in my work. So we have the or, we have the union operator, we've got the graph, we've got the inequalities, everything's there. All right, well that concludes number 18, and the final problem, number 19, is quite trivial, so I'll see you there, and we'll finish this worksheet up. All right, students, welcome back to number 19. This is the final problem of the review. Would have made it a heck of a lot easier to grade if there was a 20th problem. But nevertheless, this is it. And what are we being asked to do here? We're trying to find the domain and range of the inverse. Write your answers as inequalities and in interval notation. Well, we're masters of interval notation at this point, and we'll get to inequalities. So what's going on here? We're given a function, or we're given a graph, and we want to first find the inverse. Okay, so we don't have a lot of information to work with here except this picture. We only need to identify these 3 points. So let's do that. What is this coordinate pair right here? Let's see. -1, -2, -3, -4, -5, -6. So it's -6. What's the corresponding y value? 1, 2, 3. Okay, so -6, 3. And that's an open circle. Okie dokie. And now we have this point down here, and that is -1, -2, -3. So -3. And then this is -1, -2, -3, -4, -5, -6, -7, -8. So -3, -8. And that's a closed-in circle. Okay, so that's that coordinate pair there. That's closed. And then over here, 1, 2, comma, and then -1. Okay, and that's closed. Okay, so what we're going to do now is we're going to list this out like this. We're going to say our x and y values, x and y. Okay, so what do we have? We have -6, comma, +3. We have -3, comma, -8. We have 2, comma, -1. So this is the original function. So you can think of this as a relation graph. The inverse would just be the switching of this. So you're just going to switch the x and y values. So the inverse graph, it's just really trivial. Here's the x and y values, if you want to look at it like that, of the inverse graph. You just map the y values onto the x values. So it's the range of the original maps onto the domain of the inverse. So this is going to be 3, -8, -1. And then -6, -3, +2. It doesn't tell us to graph it, but I'm going to graph it because I want to see what it looks like. So what's my first point? 3, -6. 1, 2, 3, down 1, 2, 3, 4, 5, 6. And remember, that's going to be an open circle, okay, at 3, -6. And then we have this point. The inverse of this point is -8, -3. So -1, 2, 3, 4, 5, 6, 7, 8, down 1, 2, 3. And that point is solid. And that is -8, -3. Alrighty. And then I have -1, +2. So -1, 2, and it's a closed-in dot right here. And that's -1, 2. So I guess we can connect the dots. Let's think about how we connect the dots. So we start here at the 3, -6, and then we go over here, and then we go up here. Okay. Alrighty. This actually gives us a chance to reiterate a point that we like to make, which is that the inverse of a function is a reflection across the function f of x equals x, which is the parent function y equals x, or the parent equation y equals x. So there it is. I'm just going to write it in like that. If that offers you any help, this is y equals x. And so this is the reflection of that original function across that diagonal line. Okay, well, now we can determine the domain and range of the inverse function. So let's take a look at how they want us to do that. So they want us to write it in inequalities and in intervals. No problem. And we're just talking about the inverse here. So the smallest x value that the inverse function, the green, it's actually good that it drew it, takes on is -8. I mean, you could have read that from the list, right? So this is our inequality notation would be -8. And that is a filled in dot, less than or equal to x. And then that goes all the way over to the largest x value, which is 3. And that's an open circle, so we put less than 3. Now in interval notation, what that would look like is open bracket -8 to show that it's a closed-in circle, comma 3 close parentheses, okay, to show that that's an open circle there on 3. Now for the range, we do a similar analysis. Looking at the green, the lowest y value that this takes on is -6. Okay, so that would be -6, and that's an open circle, so that's less than y. And then the highest value this takes on, the inverse function takes on, is +2. So that's going to be less than or equal to +2. And then the interval notation would be kind of an open parentheses, -6, comma 2 close bracket, to show that that 2 is closed in dot. And ladies and gentlemen, that does it. We are done with the review. What a monumental undertaking. So at this point, we're finished with the review, and we'll take a moment to look over everything that we did and then conclude the video. So, I'd just like to conclude by looking at just the sum total of all the work that was involved in doing this. So there it is, right? It all fits in the little corner of the screen there, but when we zoom in, we just see just an astonishing amount of work that went into this, many hours of labor. And this, of course, is shared with you. You can access this through the class notebook under, I think I put it under tests and reviews. So every problem fully solved, fully explained. There will be time codes. So, at this point, it's the end of the video, so you know there are time codes. But just amazing. Now, I would say that some things we want to really focus on are the how to prove that two functions are inverses part, the rules for solving absolute values, including all the caveats that we wrote over here, absolute value equations, and then of course kind of the most interesting, intellectually speaking, were the rules for absolute value inequalities, including these cool operator symbols, the union and intersection symbols, the or and the and. So I really, really hope that this helps you on your test, because if you look at the time in the bottom right there, I'll be seeing you in just a few hours. So I'll be working furiously for the next few hours to render this video and get it into your hands, get it uploaded so you have access to it. Thank you so much for watching. It's really an honor to be your teacher. Please study this, make use of it, take advantage of what's been provided to you here, and try to do your best, do well on the test. Okay, good luck. Please reach out if you need help. Thank you so much for watching.